Alright guys, so today we're going to look at uses of certain radioisotopes, in particular cobalt and technetium. So we're looking at cobalt in industry and technetium in medicine. Okay, so what is the point? The point today is we want to be able to explain the use of one in industrial radioisotope and one medical radioisotope. And over here we see technetium in action as it is. Okay, so this is cobalt up here, and this is the radioactive decay of cobalt-60. Okay, so cobalt-60, it decays into a beta particle and a gamma radiation, or a gamma particle to make nickel. So basically use it to irradiate foods. Now, this is something that's actually really important, and it has several uses, and the main one is to sterilize food, basically. So it has the chemical property, and that is it's inert. And the question is, how does the chemical property help it for this particular use? Well, because it's inert, this means it's safely housed within machinery and it doesn't bond to it, doesn't react, so it doesn't go through oxidation or reduction. And it's also a strong gamma emitter, which is what we want it to be. So how does it work? Well, you put the food on a conveyor belt and it goes through a chamber containing essentially a block of cobalt-60. The gamma rays, they're really good at damaging large biological molecules, and this basically means DNA or large proteins. And that's because the high energy waves, they get in there and they add the energy to those bonds, so the bonds have enough energy to, I guess, reach its activation energy, and they break apart. Now, this kills microbes in your food, which means, one, they don't rot, they don't break apart. But it stops, well, because they've broken down, it stops them from, I guess, rotting the food and secreting their waste, which also helps to break down food. So the food will last longer. And it has other uses, which we'll go into a bit more of a, have a look at what we're doing in a second. So the advantages, basically, the gamma rays, they've got lots of energy, so they destroy the bacteria, but they don't make the food radioactive. So that's pretty cool. Cobalt has a half-life of 5.3 years. Now this means you can set it up in the machinery and it will last for a long time. This is important because you don't want to have to be replacing the radioisotopes too often. This is expensive and can come up with all sorts of waste. Disadvantages. Because it's breaking down these bonds in food, particularly the proteins, not so much the DNA, but the proteins, this means it will also break down some of the nutrients in food. Not enough that it's not worthwhile. We've always got to look at things as advantages versus disadvantages. There's no such thing in science, really, which is the perfect panacea. It fixes everything. So this is one of those ones where it has some positives, has some negatives, and you do a cost-benefit analysis to work out which one you're going to use. And in this case, yes, it will destroy some of the nutrients in food, just like microwaving does, or just like cooking can in general, to be honest. But it's still better to do this so that the food will last longer, food will be cheaper, we can get more food to more people. Another disadvantage is the workers need to be protected from being irradiated. Okay, so one process, multiple use. Basically, you can use it in quarantine. So if food's coming from an outside place, we want to make sure that it's not got any bugs in it or anything like this. We'll hit it with the cobalt-60. You can pathogen, so killing off all the things which might be dangerous in there. Shelf life extension. If you have a look here, there's a lot of things which are coming in from overseas. We can make chicken, meat, and fish last longer. That's really important. That's really important in making food more affordable and available to other people, but or just to those who wouldn't normally have access to fresh, healthy foods. We can kill off insects which tend to live in it, and we can also we can kill the food, which is kind of what you want. Like, you don't want food, particularly roots, that you're going to have to store for a while. You don't want those continuing to grow. You want them to be stopped growing, because if they continue to grow, well, that can cause all sorts of problems too. Alright, so technetium 99M. Here's the decay, by the way. So M means metastasized, which means it has a lot of energy. So it's technetium with a high amount of energy, releases that energy, and it becomes standard technetium 99. We use it basically to identify not just cancer, but the locations of other damaged tissue as well. But in particular, in this case, we're talking about cancer. Now, basically, because it can be changed to a whole pile of oxidation states, this means that we can insert it into a whole pile of biologically active chemicals. So a bioactive chemical is one that will bond to the body or bond to something in a cell and not interact in a negative way. So we can make bioactive chemicals with it. We can bond it to things like glucose, and then we can inject it in, and it will circulate around the body, be utilized, and will emit low energy gamma rays. Now, low energy is really important there. The reason you don't want to be high energy is that's actually too destructive. So for the human, so low energy gamma rays. Basically, we bond it to an organic compound, and it inserts into the body. Cool. It's metastable, which means it has a high excited state, which means it's going to release the photon, the gamma ray, as it calms down, which we then use to do imaging, which we'll see a few of those in a second. They actually look pretty cool. It's got a really short, so the advantage is that it's got a really short half-life, about 6 hours. If you're using something medically, this is actually one of the most important things. You do not want anything with a long half-life, because something with a long half-life will send radiation into the body for a long time. So because of this, it causes minimal damage. Low energy means it doesn't do as much damage to the cells. It's quickly eliminated by the body, and it's relatively reactive, which means it can be joined to many compounds. Okay, so we actually, this is the opposite of cobalt. Cobalt has a long half-life, which is useful for it. It's fairly inert, whereas this one's super reactive, so we can bond it to glucose and inject it into certain tissues to be used. Cobalt has a long half-life. This is a very short half-life, which means it won't be radioactive in the body for very long. The disadvantages, so because it's got a short half-life, it means it needs to be continuously made. It will also kill healthy cells. Like, it won't kill as many as if it was like high energy, but it will kill healthy cells. Very quickly, we use glucose because cancer cells are particularly greedy, and they will draw a lot. So if you inject glucose into a certain tissue, they will draw a lot of that glucose in, and they're very high in their usage of food, and it's all because of their reproduction cycle. All right, so this is what it looks like. So this is a person with thyroid cancer, and we see after 15 minutes we inject it in, and again, because those cells use such a high amount of food, it pulls the glucose in, which is radioactive, and we see a very dark spot there and there. What we see after about 2 hours, however, is that it's starting to disappear from the body, and that's cool. Now he's going to compare it to a regular X-ray. So here's a standard X-ray, and as I said, X-rays work by, when radiation hits photographic paper, which we're going to learn in a minute in the next lesson, it sends it dark. So everything that blocks it is the white stuff, and that's why the bones always look white in an X-ray. Here we see kind of the opposite. We can't really see the bones. We can see that the bones, everything here is using the sugar. Okay, so we've injected glucose into the hand. It's gone to cells all over the place, but it's concentrating heavily in here around the wrist. And this means this is where a person, well, it doesn't mean it, but it's most likely where the person has a cancer. All right, that was 2. There's a lot of information there. Good luck, and we'll see you in the next one.